Welcome back to the second lecture on functions. In this second segment, we're going to introduce a new family of functions called the exponential functions. For that, we need to have a specific value, a real value called b, which we call the base of the exponential function. Now remember that you already know how to compute b to the power n, where b is any real number and n is an integer. Namely, that's equal to b times dot 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 times b, where b appears n times. So let's call that function f of n with a subscript of b, because this function is a function of n is the variable, but it also depends on the constant b. In other words, that's a family of functions. There's one function for each value of b. And remember, we assume b is just any real number for now. So let the domain of these exponential functions be the positive real numbers, and let the codomain be the same set of positive real numbers. By definition, the exponential function to the base b is defined as follows. F sub b of x is equal to b power x. So again, this notation is well known to you. That's the same one we used here. The difference here is that the domain of these functions is the set of positive real numbers. In other words, x now can be a real number. Now, we're not going to explain in detail what it means to raise a particular real number to another real number. We can't really multiply b, say 3.5 times with itself if x is 3.5. Let's not worry about the details here. You may have seen that in your calculus course, but this is the definition of the exponential function. You need a base b, and then you give it an argument x, and the value of the function is b to the power x. So let's draw the graph for these functions. Notice, since the domain and the codomain are the set of positive real numbers, I position the x-axis and the y-axis at the bottom and to the left of the graph, so that the only quadrant that we show in the graph here is the one where all the numbers are positive. Now remember that the exponential functions form a family of functions. You get one function for each value of the base b. The easiest base to work with is when b is equal to 1, because 1 to any power is equal to 1. So in other words, the graph of the exponential function for base b equal 1 is the straight horizontal line. Now, unfortunately, that's the easiest but also the least useful of the exponential functions. So let's consider the base 2, and let's draw the graph of the function 2 to the power x. Well, 2 power 0 is 1, so the first point is here. 2 power 1 is 2, so here is the second point. 2 power 2 is 4. 3 power 2 is 9. And so let's connect those points, since the domain is the real numbers, not the integers. And here is the graph for the function 2 to the power x. Now, of course, we can increase the base to a larger value, such as 3. So let's do one more exponential function. Now, 3 power 0 is still equal to 1, so it will start at the same point right here. 3 power 1 is 3. 3 squared is 9. So here is, by connecting the points, the graph for the function 3 to the power x. It's another exponential function with a different base, namely 3. So what you notice is that these exponential functions, first of all, are all strictly increasing as long as the base is larger than 1. You notice that the larger the base, for example, when you go from 2 to 3, the faster the function increases. In fact, these exponential functions are well known to have a very high rate of increase. They quickly go up, straight up. The larger the base, the faster they go up. Hence the name exponential explosion when people talk about functions or numbers that grow really, really fast. Now, what happens when the base is not an integer? In fact, what happens when the base is less than 1, say 1/2 or 0.5? Well, let's draw the graph for that function. So let's say b is equal to 1/2. 1/2 power 0 is 1, so the function is again going to start here. 1/2 power 1 is 1/2. 1/2 squared is 1/4. And you see that what happens is the larger x is, the closer 1/2 to the power x gets to 0. So when the base is less than 1, the function is strictly decreasing and it tends to go towards 0 as x increases towards infinity. Now let's focus our attention again on the exponential functions where the base b is greater than 1, since this is the most useful case when people talk about exponential functions, are these ones. I don't want you to get the impression that these functions look similar to, say, the parabolas that we talked about when we talked about x squared. Notice these functions start a little bit higher than the parabola, but they seem to kind of look like the beginning of a parabola here. And I want to convince you that that is not the case. These exponential functions grow a lot faster than functions like x squared. So let me demonstrate this on another graph here. Notice the x-axis hasn't changed, but on the y-axis, I zoomed out, if you will, by making every square count for 10 units instead of 1. So we're counting in tens, 0, 10, 20, 30. So we're going up much faster here. So that allows me to show you a few more points on these graphs. So let's draw the function for n squared. Notice I'm switching to n from x because now I'm just going to draw the integer values. So when n goes from 0 to 9, here is the graph for the function n squared. Now this is the parabola that I was just talking about. Okay? Now what I want to show you is the graph for the exponential function with base 2, namely 2 to the power n. Notice the order of the base and the exponent are reversed in the exponential function. The base is a constant, in this case 2, and the exponent is the variable n in this case. So let's compute draw the graph for the exponential function for base b equals 2. What do we get? Well, let's start with the first point we can really see is 2 power 2 is 4, so that point would appear on top of this blue one. And then 3 power 2, sorry, I'm doing 2 power 3. So 2 power 3 is 8, which appears right under the 9 here for the square of 3, which is 9. Then the next point is 2 power 4, that happens to be 16, which again is the same as 4 squared. So notice at this point it looks like the exponential function is actually smaller than or equal to the quadratic or the n squared function. But notice what happens pretty fast. So what is 2 to the power 5? Well, that's 32. So that's already higher than the blue curve. And then 2 power 6 is 64. And that's even much higher than the blue curve. Let's do one more. 2 power 7 is 128. That will be about up here. And so I hope this convinces you that while the quadratic function or n squared function indeed follows a parabola like this, the exponential function, even with a very small base of 2, grows much faster than the parabola. It goes straight up right here. And of course, the larger the base, the faster it shoots up. Again, remember the expression, the exponential explosion, that's where it comes from. Now let's conclude this segment with a couple theorems about exponential functions. We're going to assume that x and y are any positive real numbers, and the first theorem states that if b is any real number, remember b is the base of the exponential function, then it always holds that b to the power x plus y is equal to b to the power x times b to the power y. And a similar theorem, theorem number 2, also assumes a base b, states that b to the power x together taken to the power y is equal to b to the power x times y. Now we're not going to prove these theorems. This is something you can do in a calculus class, but these are results you should be familiar with, since we may use them later in the course and definitely in other computer science courses.